Well, welcome everybody to Hydroterra's latest webinar. Today we're joined by Dana Windle, who's Technical Director of Hydrogeology at ERM. The topic we're presenting on is assessing groundwater and surface water interactions through major ion analysis and continuous monitoring. I would like to say that Dana now holds the new record for the number of registrants. It's come in at over 520. So great work, Dana, and obviously a topic of interest. I would like to begin by acknowledging that we conduct our work across this great land, and for that privilege we would like to thank the traditional owners. Hydroterra respectfully acknowledges the Boonwurrung people of the Kulin Nation where we are located today, and we pay our respects to their elders past and present. A little bit about Hydroterra. We're more than just webinars. Obviously like doing our webinars. We believe in monitoring and doing it correctly, so we're passionate about that. What have we done to help that happen? We've created a marketplace of over 100 suppliers of monitoring technology that we represent. We've built up a workshop and support and training services around that. We've got a field services team. It's all about doing measurements in the field. And we've got a monitoring systems team, which is all about integrating technologies together to create bespoke monitoring systems. So it's a little bit about us. There's a picture of our speaker. A little bit about our speaker. So Dana has more than 15 years of experience as an environmental consultant, providing technical advice and supporting environmental projects across Australia and further afield, particularly in the contaminated land industry. Dana's core technical area of expertise includes site and hydrogeological assessments, conceptual site model development, fate and transport of contaminants in groundwater, geochemical modelling and groundwater remediation, including both physical and chemical hydrogeology. Her project experience ranges from mining, power generation, manufacturing, chemical, industrial, petroleum and landfill waste projects through to greenfield sites, environmental impact assessments and due diligence studies. She's particularly passionate about using simple tools like major ions and dataloggers combined with basic groundwater level and field parameter data we collect every day to understand groundwater and surface water processes and interactions. Dana is a certified environmental practitioner, a site contamination, and also an environmental auditor for contaminated land in Victoria. A little bit more about Dana. She originally commenced her studies at Monash University here in Melbourne and went on to do a honours in that, looking at arsenic speciation in hydrocarbon-based environments and sites in Los Angeles. She did that with an organisation called URS, which is now AECOM. But it shows a really good industry university collaboration, that project. Since then, Dana's been working predominantly with URS and then now working with ERM, where she's got a national role dealing with mainly hydrogeological challenges. Interestingly, Dana manages to do all this based in Echuca, so it's a real advertisement for remote working. We love your questions. Most of you probably know this, but make sure you log your questions in the Q&A and we will do our best to answer those at the end of the presentation. Why does Hydroterra do these webinars? Well, we like you to know about Hydroterra, but we like to share knowledge, facilitate education, and take an industry leadership position. So without further ado, over to you, Dana.
Thank you, Richard. Really appreciate the introduction. And I must say it's a little bit weird for me presenting today because I've joined a lot of these webinars over the last couple of years, and it's a little bit strange being on the other side instead of listening in. But it's lovely to be here today and to be able to share these thoughts in this presentation with you all 520, 30 of you. So I've presented at quite a few conferences and industry events this year. Today is a little bit of a combination of each of those presentations, bringing together some of the key concepts. So if you've been at any of those conferences or presentations, some aspects may be familiar. I've reused or repurposed some of the slides, so bear with me if something looks a little bit familiar, but there's plenty of new aspects in there as well. Some of you will already know that using major ions is a particular passion of mine, and I'm also a very big fan of using continuous or high resolution monitoring such as dataloggers and telemetry to measure level, pressure, salinity and other parameters. I find that these are really simple and often cheap tools, but they can be really powerful. Obviously, I'm a hydrogeologist, so my day-to-day work, I tend to focus more on groundwater, but the interactions with surface water are typically a critical consideration, both in the contaminated land industry that I primarily work in, but also in natural resource management or those more clean water settings. So today, as advertised, I'm going to cover a number of items with respect to groundwater and surface water interaction. We will start with an introduction into groundwater surface water interaction in a temperate climate riverine setting, including some examples from flooding events. Then I'll go on to talk about how that same approach translates to the wet, dry season annual cycles that Northern Australia and other tropical areas experience. Then I'll talk about groundwater surface water interaction in a more coastal setting, including assessing tidal influences using dataloggers, looking at both pressure and salinity, as well as some other complicating factors to consider in that setting. Finally, I'll provide an introduction to major ions and then present a case study where major ions were used to further support the understanding of groundwater surface water interactions gained through other groundwater data. So kicking off with riverine setting. And first up, I wanted to give a bit of an introduction to surface water and some general definitions so we're all on the same page. So I'm trying to get a little bit more into AI and using some of those tools. And so I grabbed this definition of surface water from Google AI, which defines surface water as fresh water above ground, which I would argue that surface water doesn't need to be fresh, and often it isn't fresh. So fresh water above ground in rivers, lakes, streams, and wetlands, agree with that component, that originates from rainfall and runoff. Being a hydrogeologist, a little bit upset that this definition doesn't include inputs from groundwater, but I'll get past that. So a couple of things about surface water. In some ways, it can be easier to characterize and observe. It's visible, responds much more quickly to rainfall and runoff. But there can also be challenges in terms of accessing and collecting representative samples. For example, the feature of interest might be ephemeral, which means it dries up at certain times of the year or during certain years, or in high flow or flood conditions, it can be difficult accessing, or your monitoring equipment may even become damaged. Large variations in rainfall can occur throughout either the year or on a longer time frame, and I'm going to show an example of both of those. Now we'll talk about groundwater, which is essentially the water beneath our feet. So the AI definition is shown in the slide there on green. I'll read it out just for everyone. Water held underground in the pores, cracks, and spaces of rocks and sediments within geological formations called aquifers or aquitards. Groundwater originates from rainfall that infiltrates the ground and seeps downwards until it infiltrates the saturated layers. I'm generally happy with that definition, although thinking about groundwater originating from rainfall to me doesn't necessarily consider the influence of surface water and groundwater, which is obviously what we're here to talk about today. So some high-level groundwater considerations. Groundwater tends to respond more slowly to rainfall influences, although I have worked on sites where there's an almost instantaneous response in groundwater elevations to rainfall. And at the particular site I'm thinking of, that was due to vertical features like macroporing, which is through root zones or former root zones. Groundwater by its nature is less visible, so it's much more difficult to observe variations in groundwater levels and elevations. And therefore, it's more difficult to know when to monitor to capture the variability of the peaks and troughs. Understanding variability is important because it has implications for groundwater flow directions, both laterally and vertically, and it also affects groundwater surface water interaction. Groundwater is also more expensive to access through drilling of monitoring bores. And although the levels tend to vary less, bores can still go dry in the dry season or be unable to be accessed in wet seasons or high flow events. And groundwater is particularly important because variations in level of groundwater and flow to surface water can really impact on surface water quality. This is an image that I've taken from online, which I think neatly illustrates the main interactions in a riverine setting. So cross-section view across the top and then plan view across the bottom. So gaining stream on the left-hand side. Gaining streams where surface water, in this example, a river receives groundwater, which is also known as base flow. In a gaining stream setting, the groundwater table and pressure is higher than the surface water elevation, and groundwater is flowing towards that surface water feature. A losing stream, which is on the right-hand side, surface water is discharging to groundwater, or essentially recharges the groundwater, and the groundwater table and pressure is lower than the surface water elevation. So groundwater flows away from that surface water feature. It's important to realise here that this behaviour may not be static and it may vary seasonally or year to year at a particular site. So first up, I wanted to share an example of what this changing behaviour and how the dynamics might look. And I'm going to use a riverine flood in a temperate climate setting. As Richard said at the start, I live in regional Victoria in Echuca, and in October 2022, the Campaspe River and then the Murray River in my hometown flooded. So this is what the river looks like under normal conditions. This is the Campaspe River, and I took this photo on Monday when I was out walking my dogs. And in this setting, obviously I haven't measured it, but my best guess would be that this would be classified as a gaining stream. So groundwater flowing towards the river and deep-rooted trees. You can see in the picture there the famous Murray River red gums along the river accessing groundwater and surface water. And that's what the little cartoon is showing, groundwater flowing towards and discharging to the river. So under the flood conditions that occurred in 2022, the surface water level rose rapidly due to heavy rainfall in the upper catchment and overspilled the upstream weir and then the banks of the river. So on the left-hand side is the flood curve from the town upstream of Echuca, known as Rochester. You might have seen it in the news at the time. And in Rochester, the water levels rose about 5 metres in a day and a half. On the right is the manual gauging station on the Campaspe River at Echuca, which unfortunately is manual, and there is actually an automated station, but it only gets turned on in flood conditions. Something that we'd like BOM to fix if possible, please, if there's anyone out there from BOM. Just a little plug for that one. So the example on the left is what I mean by continuous data, which is collected and available from the Bureau of Meteorology, compared to on the right, where someone has to go out, visually read the gauge and try not to fall into the river. At peak flood flow, the river was flowing really fast. I actually saw a couch float past at one point. And then the river stayed outside its banks for multiple weeks. While under flood conditions, the groundwater table, again, I haven't measured this, but the groundwater table would most likely have been lower than the river and therefore able to receive outflow of surface water, with the river acting as a losing stream. You can see that in the cartoon. There also was probably infiltration into the groundwater, although it's not clear if this would have fully saturated the full thickness of the geology. But I do know in places there was air bubbling out of the roads and from the ground as the surface water seeped into the open spaces in the ground. And that photo showing the kids' playground, you can just see the little yellow top of the playground. Mm. And then the flood continued downstream, down through the Murray River, and the water levels dropped back into the river. But since groundwater is much slower to respond, the groundwater levels remained higher for longer, and you could visibly see groundwater discharge occurring into the river. So the photo there is showing iron staining in the orange and a bacterial sheen that you could see under the bridge just near my house. And at that time, there was also saturated conditions within the bank, and because of that, a lot more trees were able to fall into the river. So this is obviously an example of quite an extreme event, and how that can change groundwater flow directions and groundwater surface water interactions. But it highlights how important the changes in levels are, and how they're typically quicker for surface water than for groundwater, and then the potential implications for water quality, which I'll draw out in a couple in the next couple of examples for a more tropical setting.
Just before we move on from this, Dana, it might be worth just one thing to think about. We've been involved with these salt interception schemes, and where you've got these sort of floodplains on the Murray River, they become massive stores of salt. So for most of the year, you've got lots of eucalypts sucking water out of these floodplains, and progressively the salt just continues to build up because it's being left behind and the water's being removed. You get a flood event that comes in and creates that sort of groundwater discharge seep you're seeing there. But instead of it being fresh water, as you might expect in a flood event, it's actually, hypersaline. And so often the people trying to manage the river, they actually get really very concerned about a slug of salty water then discharging down the river over time. It really does affect the EC downstream of those areas.
Yeah, exactly. And that's sort of what you could see here, except you can clearly see the iron and the bacterial sheen. And in other cases, yeah, you'd be seeing that salt precipitate as it started to dry out if it was a salty condition. Thanks, Richard. So now I'm going to talk a bit more about tropical setting, wet season, dry season. I do a lot of work in Northern Australia, which experiences a distinct wet and dry season, which you can see compared to my hometown on this graph. So Echuca's in the green. We get much less rain, and it's a lot more evenly distributed throughout the year compared to, for example, Darwin, which is shown in the black on the left-hand side. The previous example was pretty extreme for Victoria and occurs on a decade basis. But these sort of fluctuations are essentially an annual occurrence in the tropics where there's much more dynamic conditions. So the key to note here is the strong seasonal variation, which I'll explore a lot more on the future slides. But generally what you can see in the graph on the right is at this site there, and these are all water table bores, is the rainfall is shown in the blue bars. When the rainfall starts, you get during the wet season, you then get an increase in the groundwater levels or the groundwater elevations, which peak ultimately and then decrease in the dry season. So for these bores, the difference is about 2 meters, but it's not uncommon to see much larger changes in groundwater elevations between the wet season and the dry season. Just on the next slide, please, Richard. The thing I want to highlight in this particular slide is the importance of the high resolution monitoring and what it means in terms of developing a greater understanding for a particular site. So the graph on the left shows manual groundwater level data being collected prior to 2022, and this is the pink and the purple that I'm referring to. And while you can see the general peaks and troughs in groundwater elevation with season, after 2023, both manual measurements and data loggers were deployed. And you can see that this shows much greater refinement of the water levels and highlights the timing of the peaks and the troughs, but also shows the smaller variability, which you can then compare more easily and more robustly to the surface water fluctuations, which are shown in the blue. You can clearly see how much variability would be missed and not understood if you were going by those manual gauging measurements alone. Then the graphs on the right, these are all manual data, manually measured data, but they also show how a higher frequency of monitoring can better show the trend. So in each case, the monitoring frequency, and we're looking at groundwater level measurements here, the monitoring frequency was higher at the start, so 2010, 2011 onwards. but then was able to be reduced around 27 when the trend and the interactions at these particular bores had been well established. So the graph in the top right shows periods when the groundwater elevations crossed over, indicating potential changes in vertical gradients between bores. So groundwater obviously flows from high elevation to low elevation, or high pressure to low pressure. And in this graph, you can see where the red is crossing over the yellow, for example, and the blue is crossing over the grey, which is indicating a change from either an upwards or a downwards gradient to vice versa. In the graph in the bottom right, the bore in green was shown to be consistently dry at about 23.5 metres AHD, and that's why it looks like a straight line during the dry season. And it was much clearer based on the early time, more regular monitoring, that this was the case, and it was more difficult if you had have only been collecting the data at the frequency from post 2017 or so, and you might not necessarily have understood that bore was becoming dry, and that the period of time during which that bore was dry. On the next slide, I want to highlight dataloggers and other measurement instruments are not just set and forget, though. Sometimes they do go rogue, and so periodic checks are necessary to correlate and calibrate the data that they're collecting. So the example on the left shows continuous data from a data logger, which is in blue, and the little orange dots, which are a bit hard to see, but they're the manual data measurements. And you can see there's quite a nice correlation. But the green colors show where the logger was not reading to start with. It was that showing a straight line, and there was really poor correlation with the manual gauging data. And I'm not 100% sure why in this case, but obviously there was an issue with the logger, and it just highlights the importance of those manual measurements to correct and calibrate your data. Some of the pictures on the right show level loggers at the top, which are placed into a well, and they can measure pressure, which can be correlated to water level, or they might measure water quality, salinity, EC, pH, the like, which can also be correlated to manual measurements. Being used more commonly in the industry is telemetry, which provides data directly back to the office via satellite link. I haven't used telemetry a heap myself. I know that the pros include accessibility at remote or inaccessible sites, real-time data, so not just when you happen to go back and pick up your data logger and download the data, but you can also set them to trigger warnings at certain levels. And I believe they can be integrated with new or existing sensors. Richard, I'm not sure if there was anything you wanted to add there. You would know more than me about telemetry and these sort of systems.
I could like to talk for the next 3 hours about it, though, but maybe a couple of things. So there's some standards out there from the Bureau of Meteorology that talk about minimum spot measurement frequencies for things. So depending on the application of your data, it's good to comply with those. I think the slide, that sort of graph on the left highlights the value of telemetry. So knowing when a logger has failed or maybe hasn't been started and should have been or whatever. So there's a real value in continuous monitoring where you're not regularly, in telemetry when you're not regularly downloading. I really think spot measurements are invaluable. Bunch of errors that can happen. Things like people pull the logger out to manually download it, and they lower it back down, and people used to hang them on chains or wires or whatever, and sometimes it'll be hooked around the eyelet in the well at 2 centimeters higher than it was before, and suddenly you've got this beautiful time series data that's 2 centimeters higher than it used to be, and that just doesn't happen. So it's really good to be able to check those things. So doing those spot measurements allows you to adjust those readings when you do find the error. In terms of integrating things together, the modular systems, so satellite systems these days, there's lots of different ones that Hydroterra work with, but integrating those has become pretty easy. through clouds where we do what we call API links, or we can do direct scripting to bring them back into our data hosting. So really that world has become a lot more straightforward in terms of integrating these things together. But that's probably it from me, Dana. I don't want to steal your show. So I'll go to the next slide.
Thank you. I appreciate the additional thoughts, and yeah, I was nodding along about your reinstalling loggers at different levels at different times can be challenging. The only other thing I'd just say before I continue on with this slide is the other thing to consider for larger or remote sites is accurate weather monitoring too, particularly rainfall. So rather than relying on a Bureau of Meteorology weather station that may be miles away and which may be experiencing quite different weather conditions, obviously you'd need a large site, and there need to be the value in that accurate on-site weather monitoring, but it can be hugely valuable in certain cases. Just on this slide, I wanted to touch on safety and accessibility. So I mentioned the benefits of data loggers and telemetry in the previous slide. These are two examples. So the bore on the left is, well, it looks pretty easy to access. This is in the dry season, but this area is completely flooded in the wet season, and therefore this bore cannot be sampled in the wet. And the surface water feature on the right, it looks lovely, but you can't safely access it, often because of crocodiles in the area. So just a few safety things to consider. I'm now going to talk through a typical wet-dry season cycle. On the next slide, please, Richard, and what may happen for groundwater and surface water. So surface water, we'll start with. At the start of the wet season, rainfall starts to fall. Many surface water systems will show a first flush response in terms of their water quality. So this is the same that you would see in a temperate setting after a period of low rainfall. At this time, the surface water volumes are typically low, and in many cases, the water quality produced from this runoff can be poor quality. So you might have high turbidity from washing of dust that's accumulated in the dry season, or in a temperate setting, oil on the road, dust in the stormwater system. You might have acid or low pH conditions, which can result in high metals associated with resaturation of acid sulfates generating sediments. And you could also have a higher salinity or salt load through mobilization of stagnant pools or salt deposits, which is what's shown on the picture there, where the dry season surface water has evaporatively concentrated. You can see on the graph too that the first flush at the start of the wet season, so each sort of 4 sets of data is 4 different wet seasons, that can be really difficult to capture by manual grab samples alone, which are the black dots. And the telemetry or the data loggers really come into their own here, which is shown in the green to capture that finer detail. So the start of the wet season is typically a time of little base flow, groundwater to surface water, where the surface water flow could be dominated by surface water runoff instead of base flow. Or conversely, the first flush that we see in surface water could be groundwater dominated due to catchment loading, which is an increase in groundwater elevations and discharge to surface water before there's enough rainfall runoff to produce decent surface water flows. So this graph shows that the 2 earlier wet season groundwater levels were quite high. And they were high enough that groundwater was able to discharge to surface water, which led to the higher electrical conductivity in 2020, 2021, and 2021, 2022. But then there was an operational change at this site, which lowered groundwater elevations, meant there was an improvement in surface water quality at the start of the wet season in those 2 subsequent wet seasons. I think the key point here is that surface water runoff or groundwater quality can both be a key contributor to the overall surface water quality. As the wet season progresses for surface water, on the next slide, flows continue to increase in level and volume. This typically leads to improved surface water quality during the middle of the wet season. So rainfall dilutes contaminants like acid and alkalinity, salts and metals that were higher in concentration during that first flush, or the early groundwater influences that we saw at the start of the wet season. This is an inset of that salinity graph from the previous slide that shows the improved salinity after you have that first flush or that first peak response. At this time, surface water elevations might be higher than the groundwater elevations, and there's a potential for recharge of groundwater by surface water, such as I talked through in that flooding example. During the wet season for groundwater, the shallow aquifers wet up or resaturate, and the groundwater elevations increase, particularly in the shallow and the unconfined aquifers, with meters of groundwater elevation change not uncommon. The case of the graph in the middle, there's a 4-metre increase in groundwater elevation between the dry season, and these bores are actually dry, which is why they're showing a flat line. It's not a logger issue. And then there's a 4-metre increase into the wet season. So the increase in the groundwater elevation during the wet season could be an immediate response to rainfall, or the response might be slow or lagged, and you might get a peak in the groundwater elevation occurring later in the wet season compared to the peak surface water levels and flows. So the increase in the groundwater levels may not be continual through the wet season, and you might see variability due to the variability in the daily rainfall, which you can see with these sort of peaks and troughs in the groundwater data in the green. Often the increase in surface water elevation is more subdued than in surface water. I think I said that wrong. Often the increase in groundwater elevation is more subdued than in surface water. And the increase in groundwater elevation during the wet season can be more variable in terms of magnitude and timing for different geologies and aquifers. So I'm talking about the graph on the right now, which shows groundwater level in the shallower bore, which is in blue. And the water levels there increased by about 1.5 meters, and they're much sharper, and they have earlier peaks in elevation and then a more defined recession or decreasing groundwater elevation trend. And you can compare that to the deeper bores, which are shown in the yellow and grey, where the groundwater levels increase by less, so only by less than 1 meter, and they show a much slower and more subdued response.
Dana, one thing that I've observed, well, I did my master's on it, was we were looking at near stream shallow groundwater responses, and we found that antecedent moisture conditions was a key determinant in observed groundwater fluctuations. So near stream sort of flatter areas which were close to saturation but not, they would rebound really, really quickly in response to a rainfall event. As you moved upslope, you'd have a more delayed response to them. In fact, you get a reversal of groundwater flow back up into the hill slope because of that rapid rise. So just a little aside for you.
A bit of a topographic influence as well. Yeah.
Yeah, absolutely.
Awesome.
Shall I move to the next slide?
Yes, please. So continuing through the wet season, the timing of monitoring then becomes key to capture the peak groundwater elevations so that you can assess vertical gradients and changes to those gradients, and also assess the potential for localized changes to groundwater flow direction, so within and between aquifers, and identify changes to groundwater surface water interactions, including discharge to creeks and wetlands. So in the graph on the right, the surface water feature, which is shown in blue, was initially dry before December 2023. The water level in that surface water feature responds really quickly as it rains in December and November. I haven't actually shown the rainfall. That would have been helpful. And then initially the surface water elevation in the blue is higher than those nearby shallow groundwater bores, which are in the green and black. And that means there's a potential for surface water to discharge or leak vertically to groundwater. And you can see that in the little conceptual diagram I've drawn on the left-hand side for January 2024. And at this time, the groundwater elevation was similar in both of these bores. But then later in the wet season, the groundwater elevation is higher than the surface water elevation, particularly at the water table bore, which you can see in the green. And groundwater can potentially discharge to the surface water feature. And you can see that in the changes in the cross-section for March 2024. At this time, downward hydraulic gradients from the shallow to the deep bore are also identified. And this has implications for surface water quality. Sorry. Let me pause that. Later in the wet season is when the time of highest groundwater elevations can often be seen, with higher groundwater elevations resulting in the greater contribution of base flow to creeks and rivers. And this has implications for surface water quality, assuming that the groundwater is higher salinity, which we've sort of mentioned already. So despite having the same initial groundwater elevation, the water table bore in the green and the deeper co-located bore in the black show a slightly different magnitude of response. And this highlights how the changes in the vertical hydraulic gradients between aquifers is possible. And then finally, the dry season progresses further. Surface water locations might dry up as per the photo on the right-hand side. They might form isolated pools that could then evaporatively concentrate, increase in salinity, and that's then ready to be released again as that first flush at the start of the wet season. Permanent pools that continue may be solely groundwater fed. And it's important to note that sampling at this time of isolated or unconnected pools may or may not be important, depending on the site and the connection with the rest of the environment. During this time, groundwater levels and elevations continue to fall, as we've seen on some of those previous graphs. Some bores might become dry, such as shallow aquifers, or really difficult to sample due to a limited water column. And the lower groundwater elevations and the drying surface water features might result in oxidation of acid sulfate sediments, leading to buildup of metals, acids, and salts in the subsurface, again, ready to be released in that first flush in the next wet season. So a bit of a change up now. I'm going to talk briefly about assessment in a coastal setting. So this is another example where data loggers come into their own for tidal monitoring in particular. So the graph on the left here shows groundwater elevation and tidal stage. They're in the red dots. It's a little bit hard to see, but you can see that there's a higher response in the groundwater elevation in some bores, and particularly focusing on the bore that's shown in dark blue, to the tidal fluctuations when you compare that to, say, the fluctuations you see in the purple and the pink bores. In this case, the figure, the aerial imagery below shows that blue bore is much closer to the coast, and that's the bore that's showing the greatest response. And there's generally less response and less fluctuation due to tidal influences at the bores further inland, the purple ones. So this really tells us how far inland that tidal influence can be seen. Groundwater elevations are consistently observed to be higher at the bores in pink and purple compared to those closer to the coast, which are in the green and the orangey colors. And this is consistent with the inferred flow direction, groundwater flow direction. So the groundwater elevations don't cross over in the graph, continue to be from highest to lowest, so from upgrading inland towards the coast. And there's no gradient reversal showing inwards flow to the purple bores. The second graph on the right shows salinity and rainfall. And I'm apologizing for showing rainfall. I couldn't find the graph that actually shows tidal comparison. But you can see that the bores with that lesser groundwater elevation response, pointing to the pink and purple ones, also show less fluctuation in salinity or EC, and that also supports a limited tidal interaction occurring inland in those bores. However, in the bottom right, you can see that bore in the dark blue that we were talking about, and that's actually showing on a completely different salinity axis. And that's the bore closest to the coast. And there's a nice relationship where you have peak EC and peak groundwater elevations at the time of the highest tide. So that's all coming together in a nice, neat story. But it's important to note that looking at both the pressure or level and the EC salinity response is quite important, because it's not uncommon to see a pressure response, but no actual change to EC, which might be indicating that there's no actual movement of water, and it's just a pressure response that you're seeing in the loggers.
Dana, just a question, a bit left field maybe. When you're doing numerical modelling and you've got this sort of tidal influence, is it possible, like how do you set a boundary condition? I guess it's the question. Like you've got this observed variable at your coast, like normally you'd be saying, okay, that's the boundary of the groundwater model, but how do you take into account the effective tide in that sort of scenario?
You probably have to ask a groundwater modeler, Richard, and I would not report to be one.
Okay.
I'm not 100% sure. I know that you can, in modeling, you can deal with the salinity in terms of a density component in the groundwater model. So that may go some way to answering that question, but hopefully a groundwater model on the call will jump in and pop a comment in the chat about how to deal with that.
No worries.
So the next slide, this is a different site. In this case, the coast is on the right-hand side or in the east, in the little diagrams on the right-hand side. In the graph on the left, you can see the groundwater elevations are also reflecting the tide, which is in black. but in this case, the elevations are much more similar to one another, and they seem to be peaking at different times and fluctuating to a greater or lesser magnitude. The figures on the right were generated using the datalogger data shown on the left, and these show how the groundwater flow directions can really be influenced by these tidal fluctuations. So in general, the groundwater flow directions are towards the east and southeast, which I've shown with those blue arrows. But at certain times, the groundwater can flow back into the site to the west, which is in the bright green, or to the northeast, which is in the darker green. And obviously, coming from a contaminated site background, this has implications for the migration of impacted groundwater. I'd stress also that this example shows groundwater surface water interactions at the coast, but this can also be the same in tidal stretches of rivers. So I've worked on a lot of sites, including in the Brisbane River area, where the tidal influence extends into the site. And it could even be a potential source of contamination for the site when the inland flow of river water towards groundwater is occurring. So the overall message here is this detailed understanding of tidal cycle is really important because it helps to tell you when to collect samples to best capture the groundwater that is sourced from your site and is flowing towards the coast, so low tide or possibly soon after. And it also shows that manual gauging alone might not be enough to understand the main groundwater flow directions and pathways.
Is that a sort of worst case scenario though, Dana? Like if you're sampling when sea level's lowest and the groundwater alone is discharging, is that going to create a bleaker picture than what's actually discharging?
I wouldn't say worst case, I would say most conservative, and that tends to be how we work in the contaminated land industry. You want to know the worst impacts, I suppose, and then you overlay that understanding of the tidal interaction to understand what that actually means in terms of contaminant flux. But it'll give you the worst case in terms of groundwater concentrations towards that coastal receptor, yes. So this is the same site. In this case, we were trying to understand what the different interactions may be due to the presence of a seawall, which is actually tucked around the southeast corner of the site. And that ended up influencing salinity too. So these graphs show that the salinity, and I've removed the details, just showing the colors, but higher salinity in red, lower in green. So higher salinity in the northeast portion of the site where there's no seawall, and seem to be greater interaction and inland migration inferred from the coast compared to in the southeast where there was typically lower salinity, and the seawall seemed to be limiting interaction. And but you can also see that the salinity and the pattern of salinity varied over time. Just a bit of a word of caution here and the need to think about the placement of your loggers in bores and the depth that we're monitoring too. So at this site, one of the bores, which is highlighted by the arrow on the right-hand side, the bore in purple, showed a consistently higher salinity than the other bores, but it was actually located more inland than some of the bores right along the coast, which didn't make too much sense and caused a little bit of head scratching. And then if you jump to the next slide, we looked in more detail at the bores and realized that they weren't all the same depth. So not all the loggers were targeting the same elevation. By default, the loggers were placed 0.5 meter off the base of the well. And so that meant that the logger in that deeper bore, still shown in purple there, was at a much lower elevation than the others and was targeting much saltier water. And that's why it was showing that higher salinity compared to if it had been placed higher in the water column. So the image on the left is showing a salinity profile. So we use the same data loggers that we use for the tidal monitoring. We just simply lowered them into each well and measured the pressure and level and the salinity at the same time, and then use that to create these graphs. It's pretty simple. Ideally, we would have done this before the tidal monitoring so we could refine our logger placement. But in this case, the vertical profiling was done after the tidal monitoring. So why is there such a variation in AC at depth?
Just before we move on to that.
Yep.
So in that sort of scenario, you can use, there are manual meters. So Solent's make one, it's an LTC, which you just lower down on a tape and you can read off the EC on the side of the reel. So It's often hard just using a data logger, lowering it down, bring it up, download, work out the location, but you can pretty much effectively work out your best location on the fly using one of those meters. So it's just...
Yes, very good point. Thank you. And we have used those and with good success as well. So yeah, thanks, Richard. That's very good point. Something that didn't exist when I first started in the field. So moving to the image on the right, sorry. And this is trying to understand why there's such a variation in salinity or EC with depth. This is showing the location of the freshwater groundwater interface. So seawater to the east is interacting with fresher groundwater to the west, and there's a bit of a mixing zone between them. So I've sort of put an indicative depth and location of the bores, and you could see how where the bores are located, either closer to the sea, and the depth of the bore could influence where you were seeing that groundwater surface water interaction. I don't want to go into too much detail, but I suppose overall the main message here is tidal interactions can be really complicated and they change over time too. So that location of the freshwater saltwater interface, as Richard was talking about before, isn't static and it does move as well. So very important to understand these sort of aspects when you are trying to understand your groundwater surface water interaction at your particular site.
I might just add one thing there. So done some work up sort of around Mildura and those areas, and sometimes you'll have sort of hypersaline brines that will enter into your well and they actually basically sink to the bottom. So you can end up, when you're profiling your well, you think that that's what's happening in the aquifer, but it's just been this denser water that's slowly seeped in, and you can end up with what looks like on your log, hypersaline groundwater within the formation, but it can be misleading. So well construction records become really important at that point to make sure that what you're looking at is actually what's happening in the aquifer.
Definitely. And we've also used this vertical profiling quite a lot in landfills. So looking at leachate and other sort of tailings type situations. So the vertical profiling can be really helpful, and even collecting salinity measurements as you are drilling off your cuttings can be really helpful too. So all of those lines of evidence coming together to understand your vertical profile can be key. All right, a bit of a change up now. Major ions, what we'll talk about for the rest of the presentation. So 80% of the solutes that are dissolved in water, either groundwater or surface water, are typically comprised of 8 major ions. Don't panic, there's not too much chemistry here, and I'll explain so that hopefully people are a little bit more comfortable with major ions and their use, because they're super powerful. So cations are the positively charged major ions that we're talking about: calcium, magnesium, sodium, and potassium, with other positively charged components dissolved in water, including metals, so iron and manganese, and there's plenty of others. The anions are the negatively charged ions, so sulfate, bicarbonate, carbonate, depending on pH, and chloride, with other negatively charged components and minor ions, including things like nitrate or fluoride or bromide. So in natural systems, major ions are derived from water rock interaction and other processes like rainfall, surface water recharge, or evaporation. But human activities and changes to the water balance and contamination can also contribute to or change the major ion concentrations and compositions. So I've got a couple of sneaky tips on this slide. First of all, because the bulk of dissolved components in water are your major ions, if you add up the 8 major ions and the minor ions, if they happen to be a big contributor, they should equal the TDS. So this is quite a simple calculation. Milligram per litre of all of your major ions added up should equal total dissolved solids in milligrams per litre. And if not, what that's telling you is there's either a major contaminant that you have missed, or possibly a lab error, or even things like turbidity can influence that. So you may get if you've got a high turbidity situation, you might have a higher total dissolved solids being indicated by the laboratory, which doesn't add up to all your major ions and probably wouldn't match your field measured electrical conductivity. So just a simple tip there. The other one is that the sum of your major cations expressed as milliequivalent per litre, which accounts for the charge and the weight of the molecule, should equal the sum of your major anions, since water is neutral in charge. So this is what the lab reports as ionic balance. Many of you would be familiar with that. And if that ionic balance is greater than, say, 5 or 10, it doesn't necessarily mean that the lab is wrong, but it may mean that there's another minor ion that is a big control on the charge balance that isn't being included in that standard calculation. So if you had a greater proportion of anions being indicated than cations, you're probably missing a cation that's key in that water system. Finally, the plot on the right-hand side, sorry, just back one, Richard. Plot on the right-hand side links pH to carbonate and bicarbonate. At higher pH, carbonate is dominant, so CO3, and that should be measured as the dominant anion or dominant carbonate by the lab, whereas at neutral pH, bicarbonate should be the dominant form. And this can be just a little handy check on pH in your bicarbonate carbonate data. I guess overall, major ions, I love them because they're cheap to analyze. They're only like $20 a sample or something. They're really simple to use, and I'm going to show you how, but they can be really powerful in understanding groundwater and surface water processes and therefore interactions. So people often don't know what to do with major ions, and they can go into lots of detail discussing concentrations. I find the best way to use them is often just looking at them together, plotting them visually, looking at their relative abundance or proportion, rather than looking at the individual concentrations, because that removes the influence of salinity. So there's many ways of using and visualizing major ion data. The one I tend to start with is a simple Piper plot, and they're pretty quick and easy to make. And there's plenty of different free and readily available software and spreadsheets out there. Groundwater chart, which is the snip on the slide, is a good example. It's particularly good because you don't need to panic about converting from milligrams per litre to milliequivalents per litre. You can just tick the box at the bottom, copy your data in from Excel, and it'll do it all for you. And I'll show you what that looks like on the next slide. But while we're on this slide, there's plenty of other ways that you can show your major ion data too. So shoulder diagrams, there's an example in the top right-hand corner. Durov plots, which are essentially a Piper plot, but with the addition of TDS and pH, which can be quite important at particular contaminated sites if they're players in your contamination. Or even you can just compare ratios of different parameters to one another plotted in Excel. So on the next slide, I'll explain how to read a Piper plot, which allows visualization of the relative abundance of major ions in either surface water or groundwater samples or leachate in a landfill scenario. So different water sources have different concentrations of major ions, and when you plot them as a molar ratio, waters with a similar composition plot together as a visual grouping, which may indicate a similar source of these waters. And different waters will often plot separately, and so it's common to see a mixing trend or pattern between the waters. Sometimes the differences can be really obvious, and other times they can be a bit more subtle. So just quickly, how to read a Piper plot is quite simple. If you look at the image on the left-hand side, it essentially explains it for you, but I tend to focus on the two triangles first. You look at the bottom right-hand triangle, which shows the anions. So highest proportions of sulfate at the top of that triangle, highest chloride to the right-hand side, and then bicarbonate, carbonate are grouped together in the left-hand corner. You then jump over to the left-hand triangle, which shows the cations, so the positively charged ones, dominate waters that are dominated by magnesium at the top, waters that are dominated by calcium at the left, and sodium and potassium are lumped together because potassium tends not to be tends to be a more minor cation in most waters, although there are some exceptions. And then the middle diagram shows basically taking the two triangles and extrapolating them up to meet. So you can see that in the image on the right-hand side, looking at either the bright green, yellow, or the purple, where they plot in the two triangles is then extrapolated up to the diamond in the top. And you can see that there's quite a visual difference between the black dots, which are actually a leachate sample, compared to the purple dots compared to the green, which are reflecting the different types of those waters. So just quickly, I'm going to talk through a case study if I've got time to continue on. And this is an example how major ions were used to confirm the understanding that we already had based on the contaminant distribution, the groundwater elevations, the vertical gradients, and the geology at this site to inform groundwater surface water interactions. So this shows an outline of the site setting. We're looking at an industrial site, which is the red box on the right, groundwater flowing down gradient to the west, and contamination impacts in groundwater at the two bores closest to the industrial site, so MW01 and 02. There's also a number of bores installed down gradient in this wetland marsh area where access was possible. It was pretty boggy, and that included a nested set of bores, which we focus on, being MW05, which is shallower, and MW04, which is a bit deeper. In this site setting, there's also multiple different surface water inputs. So stormwater, shown in the dark blue, was coming in from the industrial area, and that was allowing the formation of permanent and semi-permanent wetlands, which act as a potential source of contamination. There was also a creek draining from the industrial area, or a separate industrial area, which was another potential source of contamination. And then finally, there was potential interaction with the ocean and that saline freshwater interface that I was talking about earlier, through both the tidal portion of the creek and a connected salty pond, as well as through the groundwater. So the question at this site was, there's detections of contamination in the groundwater at that nested set of bores, MW04 and 5, but it was not clear if the contamination was coming from the groundwater from the industrial site or from the wetlands and the creek. So downwards hydraulic gradients were indicated from surface water to the shallow sediments at MW05, and upwards hydraulic gradients were being inferred from the regional aquifer at MW04 upwards into MW05. But there was limited data, and the potential for the reversal of the hydraulic gradients over time was also identified as an issue. On the next slide, we show some stiff plots, which a previous consultant had prepared, and these were based on a single sampling event. So stiff plots are another way to show major ion composition. Just quickly, anions are shown on the left, cations are shown on the right in each little plot, and the shape is what we're looking at here. So generally, the stiff plots supported the conceptualization and suggested that groundwater from upgrade at MW02, which is in that bright blue color, was dominated by sodium and chloride, so the pointy bits at the top of the stiff plot, with a little bit of bicarbonate. Whereas groundwater in the bores closest to the ocean, MW41 and 06, and the surface water samples from the tidal portion of the creek and the salty pond, which I'm showing in purple there, were all similar, and they were also dominated by sodium and chloride, but they had no bicarbonate, and they had higher magnesium, which is the pointy bit at the bottom left. They all have a similar shape. Surface water was different. So surface water in the fresh wetlands at SW13 down the bottom in dark blue was a bit different and had much higher bicarbonate. And you can see that in the arrow pointy bit out the right-hand side. And then we come to the two key bores that we're interested in, MW05 and 4, and they showed a mixed composition. And that supported our understanding that it was quite a hydraulically dynamic area. So the shallow bore MW05 showed a composition that was a mix between groundwater and surface water. So you could see it had the two sort of peaks of chloride and sodium, but then that bicarbonate arrow out the side. And MW04, which is the deeper bore at that location, seemed to be a mix of groundwater and seawater, suggesting the influence of the saline freshwater interface inland at this location. So we assessed this further using Piper plots and some more recent data, and also looked at changes over time. So that's the other cool thing about Piper plots. You can use the changes over time to help understand changes in processes over time as well. Color-coded on the site figure are the bores in the solid symbols, surface water samples in the open symbols. And essentially this showed regional groundwater in the red coming into the wetlands from up gradient to the east was dominated by sodium and chloride. I've sort of circled them in the diamond portion of the Piper plot up the top. There was seawater influence in the west from both the groundwater and the surface water samples. They were much more strongly dominated by chloride and had higher magnesium, so they're in the pinks and the purples. And then surface water in the wetland, which is the light blue, it's a little bit hard to see, but that showed a much higher bicarbonate proportion, fresher TDS, much more variable composition, which seem to be consistent with rainfall and surface water runoff and influences. Then in green is the bores that were on the edges of the wetlands and the shallow bore that we were most interested in, MW5. They seem to show a mix between that surface water and the groundwater, suggesting periodic infiltration of surface water near these bores. And that was really consistent with groundwater elevation fluctuations that we were seeing in those bores. And then finally, the brown, deeper bore at that nested location seemed to be a mix of groundwater and the marine composition. And altogether, this was consistent with what we were seeing in our stiff diagrams. So to wrap up this site study, essentially we've combined observations of groundwater elevations, flow directions, and vertical gradients, as well as salinity and contaminant concentrations, and using the major ion data to confirm the conceptual models. So groundwater with highest contaminant concentrations was coming into the wetlands from up gradient groundwater in the east. Those upwards gradients were causing mixing between the regional groundwater and the shallow groundwater beneath the wetlands at MW4 and 5. At the same time, surface water from those wetlands was also recharging the shallow groundwater at MW4. And that's important because that could be either a source of contamination or it could be acting to dilute the contamination. And then further contaminant dilution and seawater interaction is occurring at depth down gradient to the west due to tidal interactions in both the surface water and the groundwater. So overall, the outcome was that groundwater from the site was not discharging to surface water at the nested bores, but is discharging to shallow groundwater. And why does all this matter? This has really allowed focus of further investigations and risk assessment in this area. All right, last slide. So in conclusion, hopefully what you're going to take away from the presentation today. So groundwater and surface water interactions are dynamic. They vary seasonally and year to year. The response to rainfall is different for surface water and groundwater in terms of timing and magnitude, and that can have implications for groundwater and surface water interactions, which means that assessing and understanding them both can be challenging, but is very important. The timing of monitoring is critical. Some bores may go dry in the dry season and may not be able to be sampled. But it's important to be able to capture the peaks and troughs of level and quality, particularly in tidal cycles. So the other thing to consider is in coastal settings, there's vertical differences in salinity, which may be quite important too. Dataloggers and telemetry are a potentially cheaper or higher value approach to assessing these interactions in detail. High resolution monitoring can be really important to capture these vertical gradients, hydraulic gradients, and changes to flow directions that you can't capture through manual gauging alone, but just a note to check and compare those monitoring data to manual data. And loggers and telemetry can also provide benefits in terms of safe access in challenging or remote situations, boggy ground, flooding, or capturing extreme events like floods. Hydraulic gradients, flow directions, groundwater surface interactions may change over time. They might reverse seasonally on a daily cycle in a tidal setting. This has important implications for quality, and so it's important to characterize these changes over appropriate timeframes. It's also important, therefore, to design site characterization, assessment and monitoring programs based on a robust conceptualization of groundwater and surface water and the processes that are occurring in both. And finally, major ions, I feel, are a very valuable tool to support understanding of groundwater surface water interactions, and I think we should be using them more, and I hope this encourages you to do so. Thank you very much.
Thanks very much, Dana. That was awesome. We have plenty of questions, so I'm going to charge straight into them. If anyone needs to leave, we will be, the recording of this will be on our website on Monday, so you can catch up on them, but it's great to see so many people still here. So, thank you from Dana. Now, we had some early bird questions. Number one, any potential mitigation practices for regional drawdown where drawdown impacting near surface GDEs, groundwater dependent ecosystems? That's right.
Yep. So I've worked on a couple of projects where groundwater extraction for coal mining in particular was resulting in regional drawdown, and that was either due to a single mine or also cumulative impacts from multiple mines in the area. As Richard's just defined, for those that aren't aware, GDEs are groundwater dependent ecosystems. And that can include terrestrial, so vegetation that accesses groundwater, or also aquatic, where groundwater is contributing to the base flow or feeding a lake, for example. So in this question, I think they're asking about drawdown, lowering of the water table, which is reducing the availability of groundwater for the vegetation, or possibly reducing the flow into a surface water feature. And it might even change that surface water feature from gaining to losing. So the mitigation measures, they'd really need to be specific to that local GDE in question. Aspects that I would be considering would relate to how reliant that GDE is on groundwater, and if that's a permanent or a seasonal reliance, or it varies over time. But at a high level, and without knowing more details around this question, mitigation measures that you could consider are things like watering the vegetation, so providing surface water if that's lacking. And there may be a quality component in that as well that you might need to consider, or providing additional surface water flows if it's an aquatic GDE. Or you may need to be considering injecting groundwater, such as like a managed aquifer recharge system or the like. I think monitoring is key to understanding those influences so that you can develop the most appropriate mitigation measure, and understanding how reliant those GDEs actually are on groundwater. And then there's other options if you can't manage that. So there's things like vegetation offsets and the like, which you may need to consider.
Good. Number 2, have you used oxygen and hydrogen isotope analysis to assist with understanding groundwater dynamics? If so, your thoughts of this tool?
Yep. I can't talk to this too much. I haven't used isotope analysis much myself. I've been exposed to it on a couple of different projects, and I know it can be hugely valuable depending on the context. So there's a range of different isotopes, obviously, that can be used depending on the age of the water or the processes that you're trying to understand. And I know it's used a lot, for example, in Great Artesian Basin, trying to understand age of groundwater and groundwater surface water processes there, and coal mining areas of Queensland. The other thing to consider with isotope analysis is constraints around cost. It can be quite expensive, and also the limited laboratories that can do that analysis in Australia. And at the moment, I believe from a conference I was at recently, that there's quite long lead times for that analysis. So they're my high-level thoughts on isotopes. Definitely not an expert, unfortunately.
Useful tool if you can afford it.
Yeah.
And it's question number 3. Are there decisions flowing from what is discovered that will make for better financial outcomes for water users?
Yeah, this was an interesting question, and I really appreciate it, actually. So I suppose for me, this question was, well, what does it all matter? Why do we care? So understanding the groundwater and surface water interactions and the conceptual model for any site is, to me, the basis for then making decisions. So in a contaminated land context, if you understand these processes, that would help you to target areas of risk or remediation, which could potentially have financial impacts and benefits. So less risk, less remediation, that sort of thing. In a more natural resources management context, which I think is probably where this question's coming from, the understanding of the groundwater surface water interactions and the site in general can be really important for water allocation. So it's not an area that I work in a heap, but for example, if you understood that most of the water in a river was being provided by groundwater, then allowing large-scale groundwater pumping near that river is likely to influence the base flow, and therefore the surface water in the river, which could have both water quality and flow implications for the river, and then impacts on users of that surface water. So in my part of Victoria, there's a lot of discussion, and I don't want to get into the politics of it, but there's obviously financial issues and considerations around environmental flows versus equitable, sustainable use of the water resources for irrigation and the like, both groundwater and surface water. But for me, you can't really be making those decisions, those financial decisions and the water allocations without having the scientific understanding of the interactions that are occurring. So hopefully that's answered your question. Yeah, feel free to add more, Richard.
So I just think maybe the salinity side of things is worth discussing there. So those salt water interception schemes along the Murray River put there to limit the salinity of the Murray River and therefore improve its utility. So it used to be there was a rule that if you could reduce it by 1 EC unit, it was worth $1 million. That was sort of how they did it. This is going back 20 odd years when I was working in that area. So that's all about understanding your groundwater surface water interaction. This saline water is coming from those aquifers and it's being pushed out into the Murray River. So understanding the degree of that interaction and its impact on EC really requires those conceptual models that Dana's been talking about. We better keep moving though, Dana. Question number 4. What threshold levels in pressure and salinity should be used to manage risk and trigger management mitigation strategies?
Yeah. So threshold levels, whether you're talking pressure, salinity, or other specific contaminants or parameters, that's really got to be a site-specific question and really reflect the source or the contaminant or the issue, and then the receptor or thing that you're trying to prevent or manage risk to. As I've highlighted throughout this presentation, there's benefits of telemetry in that you can have trigger levels defined and then you get alerts in real time, which can help with that. So an example that I was thinking about is a site I work on where they have an automated monitoring system that measures salinity and turbidity in a sump, basically, and they can only discharge below a certain trigger value for both of those parameters. And they've got sluice gates that open when that monitoring says the water quality is okay to discharge to the nearby creek, and then they close when the water quality exceeds the limits. So that I really can't talk to too much more detail because that's really a site management, a site-specific question in terms of, your specific contaminants and COPCs and the risk and the receptors that you're dealing with, but just a few things to have a think about there.
Right. Question number 5. Please comment on the use of ionic traces such as silica to detect submarine groundwater discharges in coastal waters.
Yeah, so I'm not too sure about silica in particular as a tracer. Chloride, bromide, isotopes, all those other different traces I'm probably more familiar with. And I'm sure there's plenty of others. As I said earlier, the submarine groundwater discharges and that tidal interaction with coastal waters, they're never easy to measure or pinpoint or understand. It's really quite a specialist field, and I would not purport to be an expert in that area. I understand the specific location of discharge will really depend on a bunch of different factors, most likely the geology, as well as the tidal strength and the cycles. But I'm not sure there's too much more I can add to this specific question. I'm sorry.
One technology that's being used more these days is those optical fibers that can measure temperature variation, and often there's a temperature variation between your sort of marine coastal waters and your groundwater, and so you can actually lay these optical fibers down and detect the groundwater discharge areas. So that's something to think about. Number 6, please talk about groundwater on the Nullarbor and in shattered rock like the Adelaide Hills. Well, hopefully this is an area you know about.
I love this question because I really don't. So groundwater in the Nullarbor is not something I've worked on, to be honest. my basic understanding is that there's quite extensive karst and cave systems in that area, or at least in parts of the Nullarbor, which is a pretty unique groundwater setting, and therefore I'm going to assume very unique groundwater surface water interaction, as well as GDEs, subterranean in this case. It was funny because earlier this week I was actually listening in on some presentations by some students in New South Wales, and quite a few of them were studying the specific rainfall groundwater surface water contributions in cave systems in New South Wales. So very similar, and they were measuring drips from stalactites and the like, which is quite interesting. But unfortunately, I can't talk too much more to the Nullarbor. And the shattered rock, I'm not familiar with that term. I'm going to assume maybe you're referring to fractured rock, and groundwater and fractured rock in the Adelaide Hills. Again, not somewhere I've worked extensively. We've got a lot of fractured rock in Victoria too, either at depth. I have worked at fractured rock settings where fractured rock's more exposed in the high country of Victoria. I know it can be key areas of groundwater recharge. Main thing I'd say with fractured rock is it can be really difficult to assess and characterize flow paths and connections. And the variability in fracturing and the fracture orientation can be quite key.
Very good. Number 7, can the techniques you are discussing be used to assess contaminant mass flux from groundwater into a surface water?
Yes. So we often use these sort of tools, dataloggers, major ions and like, to understand groundwater surface water interactions, and then combine that with the contaminant distribution so that we can define and design specific mass flux assessments. So a couple of the examples I presented, we were actually we're trying to understand the groundwater surface water interactions so that we could then better understand the mass flux from the stormwater, so surface water to coastal setting, and also the groundwater component to the coastal environment, and the relative contribution of those. So mass flux can be both, I think the question is specifically about groundwater, but you can also be thinking about mass flux from a surface water point of view. So you're trying to understand the volume and the concentration to get to your mass flux. And the surface water, groundwater, the tools and the understanding that I've presented, it allows you to know where to sample and when, and then you can use your concentrations combined with your hydraulic gradients, hydraulic conductivity to calculate your mass flux. So for example, along a particular transect, and there's a whole bunch of different tools that you can use for that calculation. The mass flux toolkit is one, and there's also passive flux meters and things like that can help. So I suppose the tools that I presented as sort of an underpinning that can feed into that additional mass flux assessment.
Number 8, please discuss redox cycling at the discharge zone, especially in tidal conditions.
A bit of a tricky one, this one. So as I've said earlier, I feel that discharge zones in coastal settings are a pretty sort of specialized area, and also really site specific too, depending on the geology and all sorts of factors. From the question, sort of making me think that the site that they're talking about, there might be a redox difference between groundwater and the coastal area. So maybe you've got high organic carbon or high vegetation or something that's leading to lower redox potentials, perhaps. And redox obviously has implications for metal mobility and speciation. So without knowing the specific question or the specific site that you're talking about there, I'm not sure I can add too much more in terms of the specifics of redox cycling, unfortunately. It sounds like you might need to have a specific presentation on discharge into coastal settings, Richard.
Redox. I apologise if the viewers here who's requested clarification from a previous webinar. Just going to move to the, whoops, sorry. Got to get the questions up. For some reason they're not showing up. Bear with me, team. sure why I can't. Ah, there they are. That was a bit of a panicked moment. Oh, disappeared again. Bear with me. Okay. We have 16 more questions. We're going to have to go to rapid answer mode. Dana, here we go.
Awesome.
Okay, can you share again the minimum requirement for monitoring mentioned, Richard? Yep, so that's the Bureau of Meteorology's national industry guidelines for hydrometrics. So they're not like your traditional, I guess, NEPMs and things. So what I might do is will send a email out to everyone with that reference, but they're good. They also provide recommendations on minimum metadata for taking measurements. What does that mean? Things like the things that Dana would be recording in the field when she takes a measurement. That sort of thing. So they're very good. Not many people know about them, so I keep mentioning them, but they're really good. Next question, Alexander Williams. Is barometric loggers required when measuring water level? When downloading data logger, is it important to first manually do manual dips? When redeploying the logger at different depth length, how do you truncate the data so that the next reading taken overcomes this error, e.g. shortened cable? I could answer that, or you could answer that, Dana. Do you want to go?
Feel free, either or.
Well, maybe just on the use of barometric loggers depends on the type of logger. So there's two types of pressure transducer. There's what we call vented and another one called absolute. If it's a vented logger, you don't need a separate barometric logger. If it's an absolute logger, you do. Things like the picture of the solence level logger is an absolute one, so you need a barrel logger to compensate for that. Vented, you don't. When downloading the data logger, is it important to first do manual dips? Yes, 100%. Do it before you pull the logger out. Otherwise, you're creating a mini pumping test sort of scenario. So do the dip before you remove your loggers. When redeploying the logger at different depth length, how do you truncate the data? Well, you need to have your dip measurement, and you can use your dip measurement that you did when you first removed your logger as the point of truth. Or if you're removing it for a long period of time, you need to do another manual dip measurement at the time of placing it back in. That's how you can do the adjustment. Next. Oh, did you want to add anything to that, Turner?
No, it was exactly what I was going to say, but probably better. So thank you.
Bang on. Well done, Richard. All right, Alexander Williams again. What tools can be used to measure surface water elevation as distinct from groundwater elevation using bores and loggers?
I can start, or you're
Yep.
probably better in the surface water setting than me. But typically, when we've looked at surface water elevations, we've actually often created what we call a stilling well, which is essentially a kind of a false bore using a bit of PVC and screen into a surface water feature, so that we've got a set elevation and measurement point, and your logger is protected from everything that's happening in the surface water, so boats and bits of tree floating down the river and stuff like that. I'm sure there's much more sophisticated equipment that Richard could talk to as well.
Yep. So there are several methods. I'd actually probably steer towards our website, to be honest, because there's quite a few different technologies for it. Some which are contactless, which are really useful. So you can keep things out of the water, and on a lot of sites where you get big storm events and that sort of thing, contactless sensors are really valuable. You can even get contactless sensors to measure flow these days. So that's something else to be aware of. A lot of sites use Dana's approach as a backup. So I a lot of the government sites will have something like a level logger deployed. So when a big flood event comes through and cleans out everything, including the telemetry, etc., they have an alternative data set that they can use as a backup. But it's a pretty long question, to be honest, and happy to maybe run a webinar on surface water level monitoring, or just have a look at our website. There's a whole bunch there. Next question. Hi, Richard. The floodplain salt balance is influenced by residual salinity of the ancestral inland sea of the Murray-Darling Basin and agricultural fertiliser salts. Impact of eucalypts on salinity slugs is relatively minor from my experience in Murray-Darling Basin. Welcome your thoughts. No, I think we might take that one offline. Unfortunately, it's come up as an anonymous attendee. I think they probably all play a function, and it's a bit about looking at the water balance and the functions that are leading to the salt accumulation. So not much the original source of the salts, but why they're concentrating up so much. But I'm sure we've probably both got some elements that are correct there. Next question, coastal setting. Why is the green bore not as affected as the blue bore? Come on, Dana.
Well, I'm not sure which exact site you're referring to there. I think it might be the first one where there were two bores quite close to the coast, one on the east, one on the west, and there's different seawalls, which I think is the reason for those different influences.
Hey, thanks, Dana. Great insights, well presented. In dynamic natural ecosystems, there would be cycles of flows and concentrations in response to climatic variability and tidal effects. Are you able to assess whether your observations are indicating threshold events?
Yeah, it's a good point. Often we undertake our monitoring for a week or 2 weeks or the like, and that's obviously a snapshot in time. And those tidal variations do change throughout the year. So larger tides versus smaller tides, that sort of thing. So I think that's what this question is talking about. And yes, we just need to acknowledge that as much as we'd love to monitor a tidal cycle for 2 years or the like, and those longer term influences, sometimes we can do that, and other times, depending on the setting, and I'm talking from a contaminated land point of view, that may not be applicable or may not be possible. So I guess that's just important to understand the limitation of that temporal snapshot in time. But good question, thank you.
Next question from Tracy Anton. South Gippsland, impacted by Bass Strait oil and gas extraction, has not been assessed for seawater intrusion into coastal aquifer bores. This is deliberate for no data, no evidence, but will sea level rise exacerbate this?
I have done some work down that part of the world, and it's not an easy answer. It depends which aquifer you're looking at. There's the water table, and then there's the deeper confined aquifers, and there's obviously a lot going on down there in terms of oil and gas and coal mining extraction and the like, and on a catchment wide Gippsland Basin scale. Sea level, I'm guessing, will have an influence, but in terms of how far inland and how extensive, I wouldn't like to comment on that. And I'm sure there is work being done around that area.
There's some numerical models of the whole area, aren't there? Justin Dury, have you worked on so many jobs where the client just can't see the value in automated data capture and monitoring? Any suggestions to convey to clients about how much better their data will be?
Yes, it's something that comes up a lot, either from other consultants, clients alike. Do we really need this? What additional value is it going to bring? Hopefully I've been able to show today how valuable some of this data can be, And there's probably a bit of a misconception out there that all these tools are really expensive. And a lot of this technology is getting cheaper and cheaper. And in the case of telemetry and data logs and things like that, they can be cheaper as well as better than your manual measurements or the cost. It's not just a cost question, it's a value question. So that's probably how I try to answer quickly, because it's 2:00. That's probably how I'd frame that discussion with your clients.
One other thing I'd say is that we now offer a lot of telemetered solutions for rental. So if it's for a period of 6 months or something, it's more cost effective just to do it that way. So keep that in mind too. Next question, Amanda Goiviana. Have I got that right? Slide 31. Would that relationship of EC and depth be different on inland scenarios, e.g. bores connected to deep lead or rivers?
I think that
Tricky question.
yes, I think that question's talking about mixing processes and the tidal, the major iron example I used. Each site is going to be different. So yeah, I suppose overall I'd suggest that the relationship between EC and depth is important to measure on a site-specific basis and understand that on your specific site and setting. Sorry, that's a bit of a trite answer, Amanda.
It's important to understand the stratigraphy, I suppose, and the well constructions. What I've found, like the salinity example, where you can have the hypersaline waters flowing down to the base of your well, for example. So it's important to understand that part of it. Isabel Simonson, could multivariate statistical analysis provide deeper insights into groundwater data and trends than the methods we currently use?
Hi, Isabel. Isabel's in our Brisbane office, so thanks for the tricky question, Isabel. I definitely think we could be doing more with statistical analysis in general and multivariate statistical analysis as well. It's not something that I'm particularly experienced in, but yes, I think particularly with AI and all those sort of tools, we are becoming better at looking at our data and assessing trends using these sort of tools and statistical approaches. So probably a little bit outside what I'm talking about today, but yes, agree.
Alison Reynolds, for tidal sites, what recording interval do you suggest for the loggers? I generally say start with 15-minute intervals and see what the data looks after the first download, but I'd be curious to hear your thoughts.
Hi, Alison. It was really nice to meet you the other day too. This is like a bit of a catch up with everyone. It's lovely. It kind of depends on how long you're going to leave your loggers in for too. So in terms of your logger capacity, that's something I always encourage our field staff to check. There's no point starting at a really high interval if your logger's going to run out of capacity or memory before you get to the end of your intended logging. I often start at 5-minute intervals, but it does also depend on the tidal cycle. So Southern Australia has different tides to northern, western, eastern, same thing. So it depends if you're getting 2 tides a day, 4 tides a day, massive tidal variations. So again, site specific basis, but yeah, 5 to 15 is probably what I'd start with. And again, it depends what you're seeing in your groundwater and your tidal data as well.
All right, nearly through. Next question, Ivan Waromi. How can we effectively balance regulatory groundwater compliance requirements with internal performance targets? It's a tricky question.
Whoa, Ivan. Well, regulatory groundwater compliance, I'm not sure you can balance. I think you have to be working towards those all the time. So I'd probably say it's not about balancing them. It's about alongside those regulatory compliance, looking at your internal performance targets and what that means for your site specifically.
I think at the end of the day, that's what the process of developing up a site monitoring plan is, and those exercises that people go through is to align those two things. So you might have some operational metrics that are on top of that, but a lot of it's going to be driven by the ultimate end game of meeting the compliance requirements. Next question, Melinda Morris. This has been an excellent practical presentation. Well done, Dana. Great work. All right, Ivan's back again. In the context of groundwater and surface water interactions, can major ion assessments, Piper or stiff diagrams, be used to assess or quantify groundwater contaminant loads to receiving environments?
Hopefully I've convinced you that yes, not Piper diagrams, major ions can be hugely valuable in understanding the interactions. In terms of quantification, I'd probably say semi-quantitative. You can't necessarily use your major ions to tell you how much chlorinated hydrocarbon you're going to have, for example, because those two groups of chemicals will behave differently in the environment, in different interactions with the aquifers and with your waters themselves. So I suppose all these bits and pieces come together, your groundwater levels, your flow directions, your geology, your major ions, to help you understand what's going on. And then I'd overlay your contaminant loads onto that as well. I think it's a little bit similar to the mass flux question that came in the early bird question. So informing each other to a certain extent.
David Thompson, again. Thanks, Dana and Richard. Very good. The chat is deliberately disabled, by the way. Next question. Alison's back again. Not a question, but fantastic prezzo. Absolutely agree on the use of major ions to understand risk for contamination assessments. There's such a cheap analysis for the payoff.
Thanks, Alison. Fully agree.
And I believe that was the last question. So, Dana, thank you so much, and thanks to ERM. Really appreciate your presentation and sharing that knowledge. I thought it was fantastic. So many thanks.
Great. Thanks, Richard. Thanks for the opportunity. And thanks, everyone, for joining us.
And well done on the record. Might only last a week, but no, that's great. Thanks, Dana.
Thank you.